Thank you for coming to the fourth day's lecture. And so this is, according to the plan, it will be on the unit roots and supercongruences. So it will be the p-adic aspects. And I would like to first record the Morita p-adic gamma function. So this is the gamma function you first define for natural numbers. So the way you define it's actually closely relating to the properties of gamma function. So p is a fixed prime number. And then the definition will be depending on which natural number you put in, there is a sign. And then you take a product of all the entries between 1 and right smaller, a minus 1. Oh, a minus 1, so you look at the consecutive integers. If it's not a p power, you put that in. So this definition can be extended to ZP just by approximation theorem. And the convention will be when you get to 0, the value will be 1. So if you look at integers, so this value by default over here will be invertible elements. Right? And the properties coming from the definition, and I have mentioned that at 0, the convention will be 1. The functional equation, we should kind of use the fact that it's very closely relating to gamma function. For gamma function, it's gamma of x plus 1 over gamma of x. What you get is 1x. Right? Here you have a sign. And then you also have an ambiguity between majority of the cases, it's the same, it's x. And if it's divisible, if the norm is less than 1, you get minus 1. There is also the refraction formula, which is kind of similar to the case for gamma, which is gamma of x, gamma of 1 minus x, you get pi over sine of pi x. And in this case over here, what you will get more or less is plus minus 1. And this power is going to be an integer. It's unlike the traditional first digit. It goes from 1 all the way to p. And the other thing which is parallel to the case that if you use gamma 1/2 in the classical case, if you square it, what you will get will be pi. And for gamma p 1/2, if you use this refraction formula, what you get is minus 1 to the p plus 1 over 2. And there are also multiplication formulas for gamma p. The major reason that some of you know very well is because now you can write the Gauss sum in terms of gamma function, and Gauss sums have multiplication formulas. And for us, the useful thing is about the local analytic properties, correct? From Morita and Blaski. And basically, it is locally analytic within this range over here when the valuation of x is bigger than 1 over p plus 1 over p minus 1. That's locally analytic. So then you can do the p-adic logarithm, and it's a formal, you can define it formally, which is convergent for x in ZP as long as the p-adic norm is less than 1. So then we define the gk of a, which is the case derivative of gamma function over its normalized gamma p of a. So it's logarithmic derivative. And according to the definition, if I put the subscript 0, that means it's gamma pa over gamma pa, so it's 1. It's just by definition. And by the refraction formula, you also have GA1 and G1 of A and G1 of 1 minus A to be the same from the refraction formula. And then there are also other properties you can derive from the refraction formula. If you get to G2 of A and adding G2 of 1 minus A, what you will get is more or less like a weighted function. It's 2 over here, it's 1 square, and then there is a 2 in the front. Right. And for us later, basically what we're going to do is the p-adic variation applying to harmonic sums. So how it's relating to the partial harmonic sums? According to the definition, how it's defined, then using the functional equation, we can check that G1, which is the first logarithmic term, if you look at x when it's invertible, then G1 of x plus 1 minus G1 of x, what you will get will be 1 over x. And similarly, if you get to the G2 term, if you look at the consecutive G2 ratio, it's going to be this quantity over here. There are G1 terms. The major term another major term will be 1 over x squared, which is quadratic of the linear term up here. And as a corollary, then we know if you take the first few, say 1, 2, all the way to k, if I know they're all p-adically invertible, then G1 of k plus 1 minus G1 of k is the partial harmonic sum. So you're taking 1 over 1 plus 1 over 2 all the way to 1 over k. So you get to what we call the partial harmonic sum. And similarly, you can actually replace this one by some other rational number. Say if I replace by 1/2, which we use quite often, then what I need to check will be whether those combinations are all invertible. If it is, then you can write down this is a modified harmonic sum according to 1/2. So this is actually, we are using the properties backward because in the actual application, we see the harmonic sum. But we want to relate to the G1 function because now I'm going to use the expansion of the gamma function and use the equations coming from more or less the left-hand side. And Ravi Ramakrishna and I kind of putting together, checking the convergence range. Then for our application, when we get to what I call the pedic perturbation method, and one very kind of convenient result for us is basically we have A, which is an p-adic invertible, p-adic integer. And if I deform, so basically the perturbation means if I go around A nearby, so I'm allowing myself a power P, and then there might be some other thing in front of it, which is p-adical integral. Then the outcome will be modulo a power P. Basically, this power P, it tells you, depending on which P I have to put the kind of the condition, then modulo P to the T plus 1, T could be 0, 1, 2, or go up to 4 that we verify. What you can do is very much its expansion around this gamma P of A in the logarithmic term. So after normalization start with 1, then G1 of A times, this is the delta term. So this is the delta term, so delta, and delta to the 1, 2, or 3, depending on which k you are using. So we are actually computing modulo P, the Fourier expansions, for such a quotient, which is compare gamma P of A with, on the top, I would like to look at if I perturb this term p-adically, so adding a very small p-adic delta term, what's going to happen?
If P is 3, is it true? I mean, okay, so I think
if P is 3, you have to be careful, yeah.
Maybe it's just true for T is 0 and 1.
We have seen examples. It's kind of one example. If P is 3, there's it's kind of the only case certain congruences do not satisfy. But if you go beyond the range, it's because basically we need to put together to make sure the combined range over here will be big enough to make the claim. So the other thing I would like to introduce, it's a very convenient notation. It's called the Dwork, or we call it the Dwork dash operation. So what it says is, now if I have R, which is in ZP, so R in ZP, and I'm going to write in terms of p-adic expansion. So the first digit will be written as R0. So this is the first digit. and then plus R of 1, P, etc. So we can write down the p-adic expansion. And the p-adic, the what dash operation will be for fixed P. What we're going to do is we're going to add R and its negations first digit. If I do that, I get a number which is divisible by P. Then I mod out by P, so I get to a quantity which is still in ZP. In my examples, my R are also rational numbers, but you can obviously ignore the rational number part to make it to be a well-defined object between ZP to ZP. So if I look at, say, two examples, if I look at one's dash operation, all right, the notations kind of might be confusing, but we are following the Dwork's work. So this is nothing to do with the derivative, all right, but by the definition, equation 2 over here. So 1, its negation, which is -1. Look at the first digit, it's P minus 1. Dividing by 2, I get 1 back. So 1 is a fixed point of the dash operation. If I look at 2, 1/2, as long as P is odd, the computation is very similar. If I look at 1/2, its negation is -1/2. If I want to get the first digit, I will add the P to the front. So becoming P minus 1 over 2. So this is an integer. And the sum will be P over 2 divided by 2, I get back 1/2. So this says 1/2 is also a fixed point of this dash operation. But if you get to 1/3, the story will be different, depending on P is going to be 1 mod 3 or 2 mod 3. The dash operation might go to its conjugate. Okay, there are two cases. So the dash operation, basically, if I pick a number which is within the range of 0 and 1, it will actually going around the orbit of the notional conjugates, 1/3 and 2/3, corresponding to 2 different cubic roots. All right. But if I put in together 1/3 and 2/3, if I take the dash operation, it will be still close as a whole orbit. I mean, as a multi-set, it's close under the dash operation. Okay. And why the dash operation will be there is because basically this is the lemma Ravi and I wrote, but the idea already in the Dwork's paper, in his famous paper called the p-adic cycles. So if you have a number, in this case over here for our application, Ravi and I fixed the number A to be an integer between the range of 0 and 1. And if it's a rational number, and I want it to be also p-adically integral. So then what we actually kind of computed is, if I computed two different kind of, I vary my value around this fixed point A, and then I make a delta term, and then I make another delta term slightly smaller down here. It's actually motivated by the gamma function property later. If we do that, if we do the consecutive ratio, and the behavior will tell us there is the gamma term. I have actually trying to explain there is the expansion for this term here. It's exactly look like the term on the previous page. And in addition, there is the rising factorial coming into the picture. In the rising factorial notation, the A on the top, I have to use the A dash, the Dwork dash operation instead of A. So the formula putting together, there is the sign, which is coming, which will be relating to the p-adic gamma function when I convert it this way. There is a p power, which is very explicit. There is this term, I can do the local p-adic expansion. There's the rising factorial. And in case the A is an integer, the formulation, it's almost the same, but this term because 1 prime and 1 will be the same, so this term drop out. And then the corresponding term will be kind of modified accordingly. And what I want to kind of mention, a special case, is that when we look at A, B are rational numbers, and if we know, suppose that A minus B is not an integer, which is the primitive case, and none of them is a negative integer, and if the number in between A and B, so if I go up from A up to B, the numbers between A and B that are different from both, there is no integer which is divisible by P. I mean, basically this formula says I'm converting a gamma fraction if there is no P term used in the middle. I can write directly in terms of p-adic gamma function with a sign. All right. So basically, this page tells us that there is an explicit way we can convert. If I see gamma quotients, I can convert them into p-adic gamma quotients so that we can use the analytic behavior that we mentioned in the previous page. All right. So now I want to get to the point how we get from character sums to truncated hypergeometric series. So truncated hypergeometric series will be the key player for today's lecture. So yesterday we mentioned this is a very explicit way. If you give me a multi-set alpha consists of rational numbers, if you give me beta, which is another multi-set of the same length consists of rational numbers, and very often we put the assumption that the alpha and beta are primitive, means AI minus BJ, none of that difference will be an integer. And then we mentioned there's a formula depending on which fiber you are looking at and which finite field. The omega is a primitive, a generator for the multiplicative homomorphism, multiplicative characters in HQ, FQ. Omega generates the multiplicative characters of FQ clause. And then that's the definition for the HQ function. And HQ function, as I mentioned in the second lecture, if alpha, beta are defined over Q, then you can extend the definition to get rid of the fractional part to make it integral, so that it can be used to compute very efficiently. If alpha, beta are defined over Q, then there is a magma package by Mark Watkins, so that you can use them to compute the L functions at each P very quickly. And now, how to turn to truncated hypergeometric series. So what we use is the Galois-Koblitz formula. So it says, if you fix your P, if you fix the pi P, which is a root of this equation, x to the P minus 1 plus P, so the p-adic valuation of pi P is going to be 1 over P minus 1. And if you also choose your primitive piece root in the way which is consistent with the choice of pi P, then you define the Gauss sum. The Gauss sum turned out to be, there is two parts. There is a sign, there is this P power, and then there is the p-adic gamma P function. For instance, in this convention, if I start with 0 value, if I start with 0 value, then this value will be 0. I do not see anything, any contribution from the P power term. And then, of course, I do not see anything from the gamma P function term as well. So the term to start with will be 1. And then when K go up to, say, when K is 0, that's what we see. When K go up to 1, we do see that pi P term appearing. But to start with, there is also pi P term down here. All right. So this is a formula. You can combine the contributions. There are two parts, the P power term and then the gamma P term. you combine and put that into the formula. And then you can actually get a truncated hypergeometric function out of the computation when you modulo p powers. You will see that. All right. So using this method combined with what I mentioned yesterday, was that in particular, when we get to alpha to be a multi-set of 4 elements, the key point will be all the Ri will be within the range of 0 and 1. And I would like this hypergeometric motif to be defined over Q, and beta to be all ones. And when we know that lambda equals to 1 correspond to a rigid Calabi-Yau threefold, again, the picture will be, if you look at, this is the mirror quintic we're looking at, you have 1. If you look at the Hodge diamond, and then you have 101 for, this is the quintic mirror case. And then you have 1 and 0 and 0 and 1 over here. And then there is a, you do the reflection down here. I want to stretch out that in this particular case, the corresponding X3 is going to be 2-dimensional. And why there is a piece coming in? The piece coming in over here is from the original kind of the Dwork degree 5 family. The picture was the mirror. So it was bigger to start with. It's 1, 101, and 101, and 1. And when lambda equals to 1, you take away, there are great part coming from the algebraic cycles. You get to a structure which is called orbifold by physicists. And the corresponding motif is actually kind of the structure 1, 1, 0, 1. Right? The 1 corresponds to this particular piece down here. But anyway, using the idea I outlined yesterday, so you can actually try to identify the structure very explicitly. So what we did is we used magma package to identify this AP. So magma directly go to this piece and skipping this piece over here. And once we identify this piece by using magma and Sayre's very convenient formula, the criterion, then we go back to identify the corresponding character. And after it's done, when we put into the previous slides, which means I'm going to look at the very first arrow term, modulo P, what will be this corresponding character sum? Of course, modulo P, this term disappear. And this term, there are kind of graded pieces depending on the character. So you go from 0 to Q minus 2. And then it turns out after modulo P is exactly the truncation of the corresponding hypergeometric function value 1 when you truncate it at P minus 1. And typically, I don't have to do the truncation this high for modulo P, but it's good. P minus 1 is a legitimate kind of answer. I'm doing the truncation a little bit further. And now another thing I would like to say is there is a result of McCarthy and Papanikolaou. So what they did is actually look at the case 1/2, 1/2, 1/2, 1/2, and then 1, 1, 1. So it's 4F3. And then they look at minus 1. And there is a kind of formulas for on the character sum side, there are formulas relating to this kind of evaluation. They identify that for this case, the corresponding picture is a Siegel modular form. This is the Siegel case. Okay. All right. So let me get to the generic kind of very important and useful result of the work. So what he says now is the situation he first starting to consider, which is the construction, and his kind of a class of functions. What he's starting with is there is a kind of multi-set consists of rational numbers. And in his notation, his denominator always factorials that makes beta set to be all ones. And what he actually attained is when P is not dividing the least common denominator of all the AIs, and he used A1 prime all the way to AN prime to denote the dash after dash operation, the image of the alpha set. Then he actually claimed that if you look at the truncated hypergeometric function, so this is the hypergeometric function, you use all the AI rising factorial on the top, you use the B, which is K factorial down here, you compute that's the coefficient. And then the subscript here is the truncation. You're doing the truncation, you're only doing the sum from 0 to n. So what you get essentially for each of them, you get a polynomial. And under the assumption that P does not divide the least common denominator, this is a polynomial with coefficient in ZP. And what he said is, if you are going to put together any integer s, any integer t, and m, as long as the exponent t is bigger, greater, equal than s, if you look at what's the combined truncated sum, the truncation occurs to, there is m, which gives you additional freedom. This is the power p, correspond to the characteristic of the residual field, raised to t power, you subtract 1. So some of you might recall when we compute Stienster's formal group law. This is how he did that in a very similar manner. It's the p minus 1, or p to the s minus 1. So you look at alpha, beta, x. And on the another hand side, what you're going to use is 1 power less. All right, instead of p to the t, you use 1 power less, so it's t minus 1. And the corresponding parameter set, instead of alpha, beta, you use the dash operation applied to alpha, so it's alpha prime. Beta consisting of all ones, if you apply dash operation, it's still itself, so it's the same. And then x over here becoming x to the p's power. And you do in the kind of cross way, and on the right hand side, you do the same thing to p to the s, and then it's alpha, beta, x. On the left hand side, you do 1 power less, and then you do the dash operation to alpha, beta, and x to the p. So what happens is that the kind of cross term, if you look at the difference, it's highly divisible by p. All right, the assumption here is p is greater or equal than s. And the amazing thing is actually for all x. Is in general, you can make it even a little bit bigger depending on the choices of the multi-sets. But in general, he proved that quite amazingly, as you can think about that now, it's polynomials, but the power can go higher. So as polynomials in ZP, they will agree modulo. Uniformly, there's a power of p to the s to the front. So this is called Dwork's generic congruence, in the sense that the generic one means it's actually going to be true for all the x in ZP. So it's the generic congruence. And the next page I'm going to show you is what happens if you start from somewhere. When you start with m equals to 1, t equals to 1, you check the value x, you plug that in. If it's not 0 mod p, so which is the ordinary case. And in this picture over here, if we go back to this picture, each of those terms, each of these terms will be taking values to be units when you vary within a range p-adically near x. So then you can take, because of their p-adic, kind of taking units, taking values in zpx instead of zp, so you can take quotients. And so he get to his notion of the unit root. So in the ordinary case, if you look at the consecutive ratio in the sense that the it's at p to the s. Here is p to the 1 power less over here. On the top, you put your alpha beta, which is all ones for beta and x in. And in the denominator, you put the alpha under the dash operation. You put the beta, you put the x to the p. The ratio is going to be a p-adically uniformly convergent function. It's referring to as the p-adic unit root function. And the Dwork, I misspelled that. Sorry. I noticed that it's very embarrassing. Sorry. Inspire many results, including the unit root functions for the Dwork family. The variation of unit root function for the Dwork family by JDU, which was mentioned by my colleague Bill Hoffman. And then there are also 2 recent papers on the Dwork crystals by Fritz Beukers and Marsha Wolasenko. So what I'm going to use will be the Dwork unit roots. All right. Any questions before I continue to move on?
Just one. You're assuming here the betas are all equal to 1.
Yeah.
Are there generalizations of this when betas are not all equal to 1, or they're just more complicated to state, or?
I will state that I did some of the computations in 2018, and I mentioned that. I'm glad that you brought that up.
Okay.
All right. So in the Dwork's computation, which is actually kind of important right away, is because of the role of the unit root. All right. It's actually using the unit root in part to compute the zeta functions. He did the computation very explicitly for the Dwork family when degree is 4. And let me mention about the Dwork's unit root for the cases that we are actually interested in. So going back to the 14 families of the 14 cases. Oh, my pen went to sleep again. Okay. So I'm going back to the 14 one-parameter family of hypergeometric Calabi-Yau threefolds. And they can be written down very explicitly by algebraic equations, like this is the famous quintic family. And you can write down when the parameters are 1/3, 2/3, 1/3, 2/3, the equations of this form. Now it involves 6 variables, so it's in CP5. And there are 2 equations. So subtracting 2, so I'm getting an kind of the complete intersection. It's also it's a threefold. It's also a Calabi-Yau in the sense that the Hodge diamond is arranged in the way that I mentioned earlier. So for all those cases, 14 of them, they can be written down very explicitly. I show you 2 cases, 2 different flavors. This is a single equation. This is intersection of 2. And in the most extreme case, there are intersection of 4 equations for the 1/2, 1/2 case, 4 equations. But the key point is it doesn't quite matter how many equations I'm using. There is actually a formal group law theorem by Stienstra that I used already in lecture 2 for the Hesse pencil case. And what he used is actually take a product of all these equations and look at particular coefficients to compute coefficients for the formal group logarithm. And it can be so that in the ordinary case, you can actually use what he computed. What he computed is the coefficient. What he computed in Stienstra's paper is not exactly truncated hypergeometric functions, but they are deformed hypergeometric functions. So if we look at MP to the, say, t-1, they are not the same as the Dwork's case, but they are deformed. Kind of the Dwork truncated hypergeometric function. Truncated hypergeometric functions. And then there is a technique which is used by Fritz Beukers and Marsha Wolasenko, allowing us to claim that the ratio, what in Stienster's work, he's also taking the ratio in the same manner. And then he get to a unit root, so which is alpha p tilde in Stienster's formal group law. And using the strategy of Fritz Beukers and Masha Wolashenko, one can show that the two unit roots are the same. And that this second unit root constructed in Stienster's formal group law, Stienster gave then a meaning. The meaning that this unit root for Stienster is actually a reciprocal root of the numerator of the local zeta function of my Calabi-Yau manifold if my fiber is chosen to be defined over Q over here. For example, it's computed from the crystal link homology, the third crystal link homology. So that actually immediately tells us that what we are actually looking at the p-adic unit root. So the p-adic unit root from the Dwork through this connection, all of a sudden connected to the local zeta function. And for our case in particular, immediately we know when lambda is going to be 1, which is also the case for the other parameter when they're all 1, the unit root from the Dwork, it's also a root of, this is a quadratic polynomial, and monic, the linear coefficient is nothing but the piece coefficient of the modular form correspond to the rigid Calabi-Yau manifold. So it's a waveform modular form's coefficient. The constant term is p to the 3 because for wave 3 cases, all the absolute value have p to the 3 half. I have 2 of them. So as a consequence, in the ordinary case, the Dwork's p-adic unit root will be the same as our piece coefficient of the waveform modular form we have already identified, modulo p to the 3. So this is true for all the ordinary primes, as long as it's bigger than 5. All right, so this is why the Dwork's unit roots kind of tie to our picture that I'm going to use for my later results. Any more questions before I move on? Sorry, it's kind of messy. All right. Anyway, let me move on. So now I get back to the question Bill raised. Naturally, I asked myself is what happened if I replace all the beta to be all 1 to something more general. So I asked myself this question. And the first remark I make is if you have a multiset which is defined over Q, if you look at any P which is not dividing the least common denominator, then alpha is stabilized as a whole orbit as itself. All right, so we're going to use that. The other comment I'm going to say is if beta is not all 1s, the situation could be more complicated. And I actually did some computation in 2018, and the very first step I want to get to the truncated hypergeometric function. So I did this case with parameters. Say in a general study, what I'm going to show you is this particular example to illustrate the scenario that I discovered in 2018. So this example, in this example, I use my alpha set to be this multiset. This is my alpha multiset. The beta multiset is 1, 1, 1, 1, 1, 6, and 5, 6. I use that, or this, you can put 0, 0, 0. So then we look at this plot. So this step function that I kind of introduced yesterday, the step function kind of tells me p-adically if I look at my HP function, which is a sum of k-1 terms, and the behavior, how the p-adic kind of value goes up and down. And typically the value, because of the convention, will start from 0, there's no problem. And then the first time, it actually goes down because it sees 5, 6. So it goes down at 1 minus 5, 6, It's 1/6, it goes down one step. And then it goes up because it is 1/3. And then since 4 of 1/2 goes up by 4. And then it further goes up by the 2/3. And then it goes down because of C's, this value, which is 1/6, 1 minus 1/656. So the picture is going up and down. And in this picture, if we recall what I said yesterday, the mean will be here. The maximum will be 5. The mean is -1. And then we all know if I want to do kind of truncation, I have to actually take care of the minimal p-adic value. So in order to describe what happens in the base parameter, if I really use Galois-Robleto's formula, it turns out that the truncated version, there is a truncated version corresponding to the character sum. The character sum is not p-adically integral, so we need additional copy of p. Even though with the additional copy of p, that means I lower everything down to here. The base parameter here, instead of using 1/6, I need to use 7/6, which is, I got that directly out of the Galois-Robleto's formula. And this is a different scenario. So it tells us that if you really want to generalize the Dwork's result, the situation will get more complicated. And of course, you will ask me whether 7/6 is actually a natural choice, or could it be something, I mean, even more natural? So let me show you the next nice. The next one, it says that if I get back to what this is in my paper with Winnie Lee and Fanting 2, we use the kind of the method I described. We have the hypergeometric motif. If I put the 1 in, we can use magma package to compute things. Involve a little bit, it's trickier because now magma tells me something generically 4-dimensional. Luckily, we have Whipple's formula over finite field. So what we did was we first identified this piece, which is the middle layer of my onion. We kind of identify this piece first. After this piece is done, we do the subtraction. We compute the magma from the left-hand side. We take away what we know already. So then we figure out what's happening to the top piece. And it turns out this is the top piece. It's again 2-dimensional Galois representation. It turns out amazingly, if we compare the coefficient, the piece coefficient with this value, 7/6 down here, the agreement, they agree up to p to the 5. And this actually tells us that when we look at this step function, things going up and down, what we actually fix out will be this lower piece and then the most upper piece. Right? So we got out the corresponding kind of the, from motivic point of view, I have 4 zeros in between for this corresponding most outer layer of modular forms. For this inner layer, the p tells me there is a Tate twist. So it's 1 0 0 1 0. Right. So this last piece with 0 0 1 0 0 0. Right. So we have a decomposition of the hypergeometric motif into precise pieces using Whipple's formula in the Galois perspective. So it's actually one indication this is a right choice. The other indication is, yeah.
May I ask a question? Could you remind me what are the weights of those modular forms?
The weights will be max minus min.
6?
6.
Okay.
What you get is for the outer piece, the generic. So actually everybody, I mean, everybody's absolute value is supposed to be p to the 5 over 2. All right, this one is also okay because there is a Tate twist. All right, the weight tells you what's the expected generic, the norm of the characteristic polynomials roots. All right. And another indication is a right choice because we compute it, we call it the non-Archimedean kind of situation. If we go back to the Archimedean embedding, so then we compute the real periods. It's the same modular form. If you're doing a cycle, this particular cycle is using this modular function. We're integrating when the modular function takes absolute value 1, so going around the loop according to this modular function. Then this V6 level 4 modular form, and it's a slightly kind of change when they put them together is the same as the untruncated series. So they actually match exactly well.
May I ask a question?
Yeah.
So on the left-hand side,
Mhm.
I see what I might call the evaluation of a, well, let me put it this way. So there's a global L function
Mhm.
attached to your thing. I mean, global meaning all the primes.
Mhm. Yeah.
Now you also have L functions attached to these modular forms.
Mhm.
Now, can you say precisely that the global L function of this hypergeometric
Motif. Yeah.
agrees with the global L function of those Hecke forms? Do you have
Yeah.
a formula like that?
Yeah. So
Okay.
what it says
So
is,
let me continue. In general, you can evaluate a global L function at a special value. So you have a global L function, it's a function of S,
Mhm.
and then you evaluate it, say, at a special point like S equal 1.
Mhm.
And typically you expect those things will involve periods of your variety. So on the left-hand side, I seem to see a period coming as a
Yes.
global L function. And on the right-hand side, what you see, usually what you expect when you do L functions of modular forms, you expect periods of modular forms.
Mhm. Yeah.
So am I correct in interpreting this formula
Yep.
as, yep.
Yes.
Yeah.
Yeah. It's I mean, for this case, if you really want to kind of, I mean, one thing I want to stretch out is, in this case, of course, it's decomposable. The motif is decomposable. If you want to use the general theory, probably you need to dig into the irreducible pieces and then compare carefully term by term, the special L value, etc. Special L value, by the way, is computed certain integral from 0 to infinity. And what we are proposing over here is another kind of cycle. Instead of 0 to infinity, we're proposing another cycle correspond to this description. And anyway, the key part will be we are actually using a modular form.
Okay.
Yeah. So the local picture, this is the local P pieces picture, and the global picture, they are compatible, coming into a compatible package. All right. Okay. With that said, it's a good place to take a break.